Right. Yeah, right. Good morning. Okay, so the first talk of the day is me. The talk is called How Software Learns. This is not an AI talk, that's the next talk. Okay? I am using as a metaphor this book, How Buildings Learn. I'm going to talk about a couple of ideas from this and how we've taken a few things, there's a few things that we can still learn in this metaphor, but actually about how our software deals with time. And I'm not talking about event-driven code or anything like that. There is historically a perception that when we use the architecture metaphor, that architecture is about the organization of space. That's not entirely wrong, but it's definitely not right. In the real world, architecture is about the relationship of space with time. Since 1905, when we started unifying, Einstein started unifying space and time, culminating in general relativity, we have a concept called space-time. You cannot talk about one without the other. If you think that architecture is about spatial arrangement, you're missing most of the interesting stuff. People also think that when they're talking about architecture in buildings, that by definition they're talking about something that is static. There's a common perception that architecture is about static things, and people try and bring that into software. This is wrong on two levels. Building architecture is not about static stuff. It is about how things respond to the world around them over a particular duration. It just happens that buildings last quite a long time. But we're going to see that software also lasts a long time. So, my name's Kevlin Henney. I have a bunch of social media contacts. I've kind of given up trying to keep them separate. We are in an era of fragmentation. I would like to thank Elon Musk for causing this utter fragmentation and also helping me with social media addiction. Thanks to him, I no longer have that problem. But I am active on a number of different platforms. I kind of check in and out. So this book is kind of interesting. One of the things, there's a lot of ideas in Stuart Brown's book, some of which have made their way explicitly into software and were explicitly borrowed from the late 90s. This book was published in the mid-90s. From the late 90s into the early 2000s, and there's still some ideas here. By the way, this is also a really good book to have, because as you can see, it just makes you look clever, okay? If people know you have this book, they will go, oh, you're not just a software person. You're kind of sophisticated, cultured, educated. You don't have to read it, you just have to have it. But if you read it, there's more in store. Now, there's an interesting thing on the cover here. On the left, we see two buildings in the middle of the 19th century in New Orleans, Louisiana. They look identical. On the right-hand side, nearly 150 years later, we see the same two buildings. If you did not know that they had started out the same, you would not guess. That's the kind of time frames we're talking about here. And we already know this in software, that this kind of the change of ownership can cause different things to happen. In fact, we can actually see a couple of things. If I oversimplify this and kind of take a message here, if we create some kind of modular or component type structure with certain dependencies and connections, and we say we're going to run a thought experiment, because we often don't get to run these things in the real world twice, but run a thought experiment. If we start off with two, how will they change? Well, what are the forces that I can apply to them? I can apply different requirements, but actually I'm going to do something slightly different. I am going to apply ownership. So I've used colours here to indicate common ownership, but I've changed the ownership here. And when the ownership can be explicit or implicit, and this is actually quite important because sometimes there's a lot of discussion about shared ownership, and yes, you can still say that something is shared, but actually you end up with effective ownership, what actually happens. But what I've done in one case, on the left-hand side, is I've got horizontal ownership. On the right-hand side, I have vertical ownership. And then we run it. What happens when people have access to certain pieces of code, but not others? If they have to cross a team boundary or a communication boundary, or a political boundary within an organization, what happens? Well, you take the path of least resistance. You take the path that is easier, that involves less effort. You take the paths that are revealed to you. and you change according to that. It's nothing to do with functionality. There is this myth that the structure of software is related to its functionality. I say it's a myth because most myths have an element of truth, but they're not the whole truth. Of course, there will be an influence of functionality on the software structure, but it's an influence, it's not a controlling force, it's not a determining force. And there are a lot of design methodologies and approaches that give you this fantasy. And sometimes we like to have the fantasy because it gives us something to aim for. But in reality, most of the forces are quite different. And it will shape it, and it will shape the software, and that will shape the requirements that people then give it. So even if you started out with the same requirements, the changes of ownership over a period of years, they'll say, well, we can do that to this system, but we won't do it to the one on the right. So you end up with a different structure. You play it out through time. So this tells us the criteria, the way that our software responds to change is not solely down to an idea of requirements and simply paradigm. Now, some of you may already be familiar with this idea, so can I just have a quick check? Who knows that part of what I've described here is known as Conway's law? Can I just get a check of hands? Okay, so not everybody. So well done. Today, the first thing you're going to learn, other than it's a cool book to get, the first thing you're going to learn after that is there is a thing called Conway's law. It's named after Melvin Conway. He wrote this up in a very short paper in 1968. So not a new idea. Melvin Conway, in case you're wondering, is that his only contribution to software? Can I just have a quick show of hands? Who here has heard of the idea of the coroutine? If you're using Kotlin or various languages, coroutines, invented by Melvin Conway in 1958. So I was amused to find a blog recently, a couple of years ago, where someone said, oh yeah, it's great, I'm using Kotlin and there's this new feature in it, coroutines, or I can't remember, it might have been, I'm using Python and it's got this new idea, coroutines. Yeah, it's been new since the late 1950s. So, he's been inventing the future forever. I do recommend reading this paper, How Do Committees Invent? There's a lot of really interesting stuff in here, but it's very short, but design organization criteria. It was actually in many ways quite provocative, because he's basically saying, the basic thesis is that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. He referred to it as a homomorphic force. It is a force that says, oh, if you communicate like this, that will influence the structure of what you're going to build. It's actually, in one sense, a very obvious observation, in the sense that when people work together, the people you communicate with, well, you have a certain trust relationship. There are certain things that are going to happen. The people you don't communicate with, well, you don't have that. And of course, the way that humans work is going to influence the things that they build. In that sense, it's a trivial observation. It's a trivial enough observation that people overlook it or don't think it's important or misinterpret it. It's not and when people talk about it as a law, it's not a law you opt into. It's not like the speed limit. I choose to observe the speed limit or I choose not to. I'm from the UK, so I choose to drive on a different side of the road, but that's a choice. I could choose the other side of the road in the UK. It's not a good choice, but I have that freedom. Whereas this morning when I woke up, I didn't go, you know what? Today I will not respect the law of gravity. That turns out not to be a choice I have. So Conway's law is somewhere between these two. It is a force. It's not truly a law in that sense. Now, in this sense, he kind of drew a diagram highlighting this thing. Now, another observation, this goes through waves and cycles, awareness of Conway's law. A few years ago, an observation was made. Inverse Conway maneuver recommends evolving your team and organizational structure to promote your desired architecture. This is kind of interesting because a lot of people think Conway's law is you have this team structure, you will just end up with this software structure. Actually, this is trying to say you can do the opposite. There's only one problem. This is actually what Conway was saying. If you read the paper, this is why I always tell people, please read the paper. It's not the inverse Conway maneuver, it is the Conway maneuver. Because Conway said, we have found a criterion for the structuring of design organizations. A design effort should be organized according to the need for communication. That's the inverse. That's exactly what he's saying. It isn't the inverse. It is what he was saying. The point there read what you cite. That's another recommendation. But here is this observation. Now, we also find he was making these statements in the late 1960s. He didn't necessarily have all of the data. These days we tend to have the data. A wonderful book by Adam Thornhill, now in its second edition, Your Code as a Crime Scene. Adam looks at one of the things that I think is the most neglected. Every single system is sitting on a mine of data that it doesn't use. There's so much data every system has, and people ignore it. It's sitting in your version control system. It's the history of your system. I find, for example, the fact that people refer to version control systems these days as repos is a terrible, it initially sounds cool, but it isn't. A repo is short for repository. That's a terrible description of something so powerful. A repository is a place you put stuff. A version control system, it gets a bit closer. What it really is a time machine. It's a history machine. It's a social history machine. You can go and look at how your system grew, how it evolved. What are the things that change together? What are the things that change frequently? What are the things that don't change? What are the things that are changed by certain people and not others? Where are the boundaries of your actual teams? What is their footprint in the code? In other words, code analytics. So these days I tend to say, if you're not looking at this, you don't care about your software architecture. It's a very strong statement. 20 years ago I wouldn't have made it, but now we know. It's a case of you've got to look at what's actually going on, otherwise it's fantasy. And that's the point. And actually Adam has read the Conway paper. Even though Conway formulated his law around the initial design of a system, so therefore he formed that law, and then here's the recommendation. The law has important implications for the continued maintenance of existing code as well, which is the bit that people normally think of. So, here's an interesting thing. It's 2024, 10 years ago, Rob Smallshare wrote this really interesting post, very long post, where he talks about simulating, basically, predictive models of development teams and the systems they build, simulating how teams will work in terms of ownership. And also their contribution. So, Greenfield project, let me interpret this for you. You start a Greenfield project here. Let's develop it for 5 years. Keep things simple, we'll have a constant team size of 7. But where you see a colour stopping and changing with a line and then changing to a lighter colour, that person has left the team. Now, this is the interesting thing. They may have left the team, but their influence continues to live on. Rob's observation here is this: the state of a system reflects not only the organisation, but the organisational history and the flow of people through those organisations over the long term. He's added the time dimension. Previously, people tend to think of Conway's law just in its narrow spatial sense. As Rob says, what I mean is that the structure of the software reflects the organisational structure integrated over time. It's a temporal structure. After 5 years, you don't have 7 people working on that. You have the effect of potentially 20, 21 people working on it. And what does that look like? And that system now has these different forms of knowledge. It's effectively learnt from them in some way. But that's a very different way. We normally look at teams as a constant, as if now is the only moment that ever existed, and then there's legacy. Whereas actually legacy has a refined, deep structure. But here's the thing. This is the bit that surprises us. This is the bit that humans are very bad at. We have a terrible relationship with time. Okay, we are really not very good at it. Anybody who's ever waited for me knows this. I'm normally late. We struggle when we come to estimate things. Not just in software, but in other walks of life. Time is not as intuitive to us. It elasticates, it becomes long and short depending on our mood and the people around us. So time is a thing we have a difficult relationship with. So I'm going to refer to the Sandman. Now, some of you, Neil Gaiman is a brilliant writer, Sandman was recently adapted very effectively for Netflix, so if you want the shortcut onto this one, go and watch Netflix. That's your homework. If you really want to get into his writing, though, actually I do recommend reading the original Sandman graphic novels. But in the Sandman, there is this character called Delirium, and she's kind of like a little bit scatterbrained. And so she says, what's the name of the word for things not being the same always? You know, I'm sure there is one, isn't there? There must be a word for it. The thing that lets you know time is happening. I love that description. How do we know that time is happening? So her brother, who is the Sandman, known as Dream, and is an entity of very few words, says, change. Oh, I was afraid of that. We have a poor relationship with time. Our relationship with change is even worse in that sense. So, Grace Hopper, one of the people kind of responsible for the compiler and such things, and a woman of great insight, has this wonderful observation. Humans are allergic to change. They love to say, we've always done it this way. I try to fight that. That's why I have a clock on my wall that runs counterclockwise. It's also, by the way, why I have a clock on my... Grace Hopper is why I have a clock on my wall. That's a picture of my clock that runs counterclockwise. Because I use this quote, and a few years ago I suddenly thought, I live in the age of internet shopping. Surely there must be clocks that go the wrong way. Oh yeah, there's plenty. So I now have one on my wall. It really messes with people when they walk in my office. It's just like, what? So we have a poor relationship with change, but change is all there is. Change is the passage of time. We even try to model this idea of conservatism, that we are reluctant to change. And there is a curve that we use. Some of you may have seen this. I'll check in a moment. You have innovators. They're the leading edge. Then you have the early adopters. If a new technology comes along, we like to say, oh, you've got a few innovators here. Then you have the early adopters. Then there's the early majority. Here's where people are getting into it. Then we have the late majority. And then we have the laggards, the last people to adopt a new practice, a new tool, a new technology, a new approach. And we describe this as purely around the conservatism of human beings. And actually it does reflect that. But the way this is normally presented to us is like this. So I got this from the site. Number of adopters, technology matures. So sometimes this is called the technology maturity model. But who's already seen this? Who's seen this one before? So a few of you have seen it. It does the rounds in terms of it. But the reason I chose this site is because that's not what this curve shows at all. It doesn't show technological maturity. It shows market maturity. These are not the same. This has nothing to do with the technology. It is about how people respond. It's nothing to do with the intrinsic technology. It was actually originally formulated in the 1950s in America to understand how people adopt different agricultural practices. It's nothing to do with our traditional technology. It is about how the market and how people respond. It may correspond to technological maturity, but that's a correlation. It's not necessary. But there are things that sometimes take time. And there are reasons why some things move slower than others. We often talk about this idea that we're in technology, everything's fast moving. Yeah, I'm going to go with the Grace Hopper quote. I try to fight that. Technology is not fast moving, or rather, not all of technology is fast moving. Who's come across the TIOBE index for programming languages? It's one of the most popular ones. It's not the only one. There's the Red Monk one, and there's a couple of others. I'm going to focus on TIOBE for the moment, but it turns out that all of them support what I'm about to say. Here's the top 10 programming languages as of January 2024. Please raise your hand if you currently work with at least one of these. Okay, please raise your hand. Wrong question. Raise your hand if you're not working with one of these. Okay, that was a bit easier. Right. Now, what I want to point out here is this is a highly skewed distribution. 1, 2, 3, 4, 5, 14% down to 7%. And then there's a cliff edge, boom, down to 2%. And it's all down, dropping down to 1% and so on, beyond up to the top 50. It's got a very long tail. Just to understand what I'm talking about here, 50% is the first 5. The other 50% are in the next 45. But there's another observation to be made here. Here are all the languages that were created in the 20th century. There are 2 languages in the top 10 that were created this century. We are now hitting a point, which I find quite interesting, where statistically people coming into the industry are using languages that are older than them as a large majority. And only a couple of, C# only got in by being 2001, I think. Yeah, we're a really fast-moving industry. Well, let's look at the top 20. Yeah, kind of same story. This doesn't mean that there isn't change, it's just, you see there's Rust, there's Swift, there's Go, 2009, Rust 2014, 2015, Kotlin 2010. Yeah. This is a slow change. Not everything changes at the fastest rate. Oh, of course, individually these languages change, but the set of languages does not change very much at all. Here's Tyobe's observation on it, going back to the beginning of the century. There's a bit of movement, but there's nothing radical. You get the same from Red Monk. It turns out that there is a point here. The languages form a foundation. The applications are built on the languages. You can't change your languages typically faster than you can change your applications. The observation of the author, William Faulkner, the past is never dead, it's not even past. Now, actually, there's an interesting point there. That we are dealing with different rates of change. So anybody who thinks, oh, technology is fast-paced, that would be exhausting. It's not. There are bits of it that are, and then there are bits of it that are very slow-moving on a generational phase. Our job is to understand, again, our relationship with time and the relationship of these things to time. So, anybody working with Java or working on the JVM at all? Yeah, you're familiar with this? This is an interface in Java, clonable. Yeah, it's been there since before the beginning of the first public release. Anybody working in .NET? Okay, a few people, yeah. iClonable, yeah. Anybody working in English? I want you to notice something. So here's a bug report from 1996. Just before Java was released. Clonable is spelled with only one E, clonable. Ask any geneticist, including my wife. Very helpful to have in-house expertise that you can draw upon. Always trust the domain experts. Find a domain expert, marry them, I don't know. Ask any English expert such as Henry McGilton. Now it gets quite funny because English is not spelt correctly. And I had to look this one up. Henry McGilton is an English usage individual. I think he's American, but that's not how you spell McGilton. So I'm going to teach you another thing this morning. Muffrey's law. You may have come across Murphy's law. Muffrey's law. Muffrey's law, if you write anything correcting or criticizing the quality of someone else's editing, proofing, spelling, grammar, etc., there will be some kind of editorial error in what you have written. Yeah? You probably experienced this as well. Yeah? It's a variant of Murphy's law. So, I like this. There's a good irony here. This is embarrassing. Let's fix it before we ship. They didn't. And why? We can't fix it after, and right now very little code relies upon this typo. This tells us why it is that some things will naturally move at different rates. It is nothing to do with the intrinsic structure. Changing the spelling of clonable in a piece of code is trivial. Changing it on everybody that depends on that is huge. How much would it cost Oracle to fix that spelling mistake? 2 minutes to actually do it, commit it, and then 2 years to sort out the fallout. The same for Microsoft. It's not to do with the size of the thing, it's to do with the size of the dependency set. That's what makes it a big thing. We find this with protocols and so on. Naming is just protocols. It's the size of the dependency set. So here's a nice word. Michael Feathers observed this way of thinking about software architecture, traumatropism. Feel free to drop that into a conversation with your colleagues to sound that a little more impressive. Traumatropism is the regrowth of a plant or tree, often in a bizarre shape or direction as a result of earlier damage or trauma. Now, I've given you new vocabulary to talk about unmanaged technical debt. How would you describe your architecture? Traumatropic legacy. That's cool. Yeah? Arbitrary decisions or accidental decisions that then become, how big is that clonable decision? Let's find out. Let's go to Wiktionary. When you look at Wiktionary, this is how you spell clonable. Alternative forms, especially in computing contexts. Well done, us as an industry. By repeatedly spelling it wrong, it has become right. Okay? Repetition legitimizes. Observation from Josh Block, who used to work for Sun and designed the Java collections classes. He made this observation: public APIs like diamonds are forever. They're going to last. And they don't last because it's an intrinsic quality, they last because it's an extrinsic quality. It is about the dependencies on them. And by the way, if nobody depends on them, it's really easy to change. Yeah. So, I just said that Josh worked for Sun. When did Sun stop being Sun? Because they were around from the 1980s. And then in 2010, there was no sun. There was only darkness. Oracle. Why am I making a point about this? Because I'm showing you their domain name. And there was this really interesting thing in Java when it came out. Java was pushed as, here's an internet language. So we need a way of organizing code, so we're going to use domain names because that's cool and new and sexy. And I remember at the time thinking, this doesn't feel right. And I don't know why. And now I do. Because there are loads of packages in the Java distribution that refer to something that no longer exists. Because it turns out that Java survives, it turns out that programming languages live longer than companies. Okay? It actually turns out that products often live longer than companies, or company names. Therefore, if you have your company name in your code, well, now you know what you're doing tomorrow. You're taking your company name out of your code. That code will last longer than your company. Okay? So this gives us another understanding of change. So back to how buildings learn. He takes the work of Frank Duffy, a British architect, who analysed rates of change in functional buildings like office buildings and things like that, and made this observation that there are different layers of change. The most stable thing about a building is where it is. Now, I recognize that I'm saying this in Romania, and that Romania is one of the countries where this might not be true all of the time. That during the Ceausescu era, some buildings were moved. The site, but this is the exception rather than the rule. Okay? The site is normally the most stable, the foundation. And so people often think, oh, well, our company is the site. No, it isn't. Your company can change. I used to work with a guy who, when he was interviewed, he had 4 companies on his CV for 10 years. Over 10 years, he'd worked for 4 companies. Actually, he had the same desk. The company changed around him 3 times from the time he joined. Your company is not a stable abstraction, so don't rely on it. Okay? There are other things that are more stable. Your company is not your site. Then we have structural stuff. What we mean by structure is load-bearing stuff, the stuff that holds up the building. Don't mess with this. Then we have the facade of the building, the exterior. This can change over a period of decades, 3 or 4 decades. Then we get to the services, air conditioning, lighting, cabling. That can change on a 5 to 15-year cycle. Then the space plan, and then the stuff, the chairs, the tables, those can change every day. The point there is that you want to organize a building so that these changes are at the right level. If you want to add more air conditioning, you don't want to be pulling out load-bearing structure. You want to organize the building sympathetically. And this also reminds us, so therefore the programming language is more likely a site than your company. That's why the programming languages move so very slowly. Now, that idea of shearing layers was observed by a number of people in the patterns community. There's this wonderful paper from the late 90s, mid to late 90s, you can find it online, Big Ball of Mud. Often people know the name because they sort of talk about their legacy systems as like, yeah, we've got a big ball of mud. But now you know you've got a traumatropic ball of mud. Okay, so we've got more sophisticated vocabulary. Big ball of mud, people often remember the term, but they don't read the paper. This is by Brian Foote and Joe Yoder, and there's some really interesting stuff in here. One of the observations they make using exactly that diagram, inspired exactly by the Stuart Brand book, How Buildings Learn, is this pattern, shearing layers. Different artifacts change at different rates. Therefore, factor your system so that artifacts that change at similar rates are together. This is an interesting idea. We actually see Adam talks about it as well. Measuring change frequencies is based on the idea that code that has changed in the past is likely to change again. But let us also be very clear that what we are using is a probabilistic technique. We are not predicting the future. You cannot predict the future. What we're doing is we're saying there's a high probability this will happen. The rate of change of this appears to be that. So this is the point that I was making earlier, that with a legacy system, you have an advantage that you often overlook. Your system has a history. Take advantage of that. It gives you information that new systems don't yet have. Okay? Look at what changes. Now, this is kind of an interesting one because a friend of mine, Alan O'Callaghan, did a study of software at British Telecom, legacy code, and he also discovered, he documented a number of patterns here, but he documented under a different name, time-ordered coupling. He observed that this old software followed the shearing layers approach. Yeah. How is the high-level structure of a system best organized for adaptation in the long term? Organize the system into partitions or modify its existing structure if other concerns predominate in the architecture so that components of each of the partitions have similar lifespans or change rates. Now notice here we started off with the idea that some of the partitioning of our system will be driven by who accesses it and how they communicate with one another. Nothing to do with the functionality. Here, we've got another criterion for partitioning that is nothing to do with the functionality. Okay? It is about how does the system evolve. Observe that, almost free of the understanding of you will find that sometimes these align, and this aligns with traditional abstractions, but sometimes it does not. It can surprise us. Now, I just said you can't predict the future, so we're using the past, we're predicting the past, but there is an interesting observation here. There's another technique. I'm going to have to decode a bit because I don't think Alan explained it quite as obviously, but he talked about buffer the system with scenarios. I need to translate what that means. This is a technique from the Stuart Brand book. Stuart Brand was very interested in this idea, and he found some architects who did it, of a technique called scenario buffering. What is this? We use the term scenario in software. The idea is imagine future usage of the system. We're not saying it's going to be guaranteed, but imagine it. What will happen to your architecture if these changes happen? Okay? And see how it responds. So you're using your imagination. You're using speculation. Now, be very careful here. The idea is we're not going to use our speculation to add things. We're going to use our speculation to decide between alternatives. It's not about adding stuff. It's just saying, given two design choices, which one of these seems to be more stable for future changes? The way that Alan phrased it is, if business requirements shape software architecture, but the business context is volatile, most business contexts are, how do you start constructing a software architecture? He said, use scenarios, use imagined uses of the system. to buffer the system against the effect of such changes. In other words, try it out, just see what happens, what's stable, what requires lots of points of change. And that is a better use of speculation. As humans, we have this wonderful facility, imagination, speculation. But as software developers, we often misuse it. I'm going to build a framework. Yeah, that's what normally happens. It's just like, okay, let's add some more interfaces and plugins and this, that, and the other. And before you know it, what started as Monday is now Saturday morning. And you haven't actually done any of the work you were supposed to. Exciting as it is, it's pure yak shaving. Okay, so I'm going to pick a very, very simple example. I'm going to walk you through it just a couple of minutes. But I want to give you a sense. I'm going to use a library system, a book lending library. Can I just have a quick show of hands? Who is familiar with the concept of a library that lends books? Now, I'm asking this because a guy I used to work with, this was about 20 years ago. And Paul said, I was preparing a workshop, and he said, oh, Kevlin, I see you're using the old library example. The library example has been with us in software and IT systems workshops since at least the 1970s. It might even go back as far as the 1960s. I've yet to determine this, but it's a really old example. Lots of people use it. And I will continue to use it because the thing that Paul said still makes me laugh. He said, oh, I use a more up-to-date example. I use video rental stores. I had to explain to my 18-year-old what a video rental store was recently. He was appalled. He thought this was the most terrible idea ever. But Dad, what if they don't have the film that you want to watch because somebody else is watching it? You have to watch something else. What? Yeah, he's a child of the streaming age. So, libraries and books were good. Okay, there are people who are members, and they have a set of requirements. There's a bunch of things that they can do. They can borrow books, they can do various things. They've got various capabilities. There are people who are librarians, and they administer the library. They allow us to register books and register members. Great. We can even come up with a kind of like a simple model for this. That a library has membership, it has loaning, it has a catalogue, membership, many members, loaning has loans, catalogue. A loan is a relationship between the copy of a book and a member. Yeah, this member borrows that book. This book is on loan or it's on the shelf. And the book has a corresponding book title. If you have 5 copies of How Buildings Learn, then that is 5 copies of the book title, How Buildings Learn, okay, with an ISBN. So obviously there'll be other classes, but we're not interested in those. You just have to kind of imagine they're there, all these other little value-based classes and so on. And what we're going to do is we're going to package it up. Now, there are reasons for this packaging. I'm not going to go into it. There are lots of reasons. This is actually relatively intuitive. I run this as a workshop example. Every time I ask for packaging, almost everybody will choose this packaging. So I'm not even going to say it's that contentious. But let's take a step back from the detail. The course structure of this looks like this. By the way, I'm using packaging in a very broad sense. I don't just mean, say, Java packaging. I mean anything where you have any separation that is significant in how you organize the system. That could be a component. That could be a service. These days, modular monoliths are coming back, so that could be a component. We're reinventing component-based development. Brilliant. Yeah? You can call it modular monoliths if you like, but back in the 1990s, we used to call it component-based development. It doesn't really matter what the granularity is. You can use the term subsystem. You can use the term library. All of these are below the level of the system, but above the level of the individual units of functionality and behavior. But there's a thing about this relationship. The thing that might trouble us a little bit is there are cyclic dependencies. In other words, although these are separately partitioned, they behave as one. Yeah? Although I partition them, they move as one. If I update one, I have to update the other, and vice versa. There's no strict layering between them. You actually see this in a number of things. Let's go back to Java. Java.lang intuitively feels like the lowest level of the system, except that it depends on Java.io. And Java.io depends on Java.lang. I haven't even finished. This could go on for ages. It's basically like spaghetti when you look at the dependencies. It's like the people who designed the packages were in a different building. And the people who actually designed the relationships are in this building over here. Beautiful Conway's law comparison there. However, whatever the cause, we often find this. And there are reasons we care about this. Sometimes it's to do with deployment, sometimes it's to do with builds. But let's just say we want to get rid of these. If I maintain the object relationships, there are if I maintain the object relationships and my package choices, there are 4 arrangements that are possible. 1, main is always going to be at the root. Members depends on loans, depends on catalog. 2, catalog depends on loans, depends on members. 3, members and catalog both depend on loans. 4, loans depends on members and catalog. That's 4 choices. I can make every single one of them work. There's not a question of functionality. They all have the same underlying object model. I just put interfaces in different places to make it work. This is not a choice of what furniture you have, it's where do you want your furniture. Yeah? It's how do you want to connect the things. So in one sense it's an arbitrary choice because it has no bearing on the functionality, but it will have a bearing on our relationship to the code and how we maintain it, how we deploy it, where we notice the rates of change. When I run this, I've run this as a workshop example for many years. Most teams, most people will choose option number 4. Loans depends on members and catalog. It feels right. But you've got to use a bit more than feeling. Let's use the future. Well, we don't know the future, but we have an approximation. We have some potential scenarios or features. We can use the backlog. Here is a ready source of possible futures. That's the way I look at it. It's a probabilistic technique. It's not a guarantee, but there's a very good chance that some of the things that are in your backlog are things you will build. There's also a good chance some of them won't be built. There's a good chance that a lot of things that aren't in the backlog will be built. And there's an even better chance that the things in the backlog won't be built as you expected. But mostly the shape is right. What we can do is we can use these possible futures to actually determine which of 1, 2, 3, and 4 are going to be better. And it turns out that 3 is the best choice. And very few people choose 3 in comparison to 4. It's very rare people choose 1 or 2, but very few people ever choose option 3. And we can actually find out why. Because when you look at it, and you just go through each feature, and you just put a dot, so this is a whiteboard technique, and I've used this with teams. Draw up a quick sketch of how you think about your system. Go through some possible requirements. Everywhere you think you might touch code, put a dot. And you build up a heat map. The thing that doesn't surprise us is that the entry point to the system, the one that exposes the functionality, is the least stable. That's fine, it's up at the top. The most stable thing is the loans, though. Loaning is the most stable concept in the whole system. We put that at the bottom according to shearing layers. Now, in terms of the interfaces, if we started with something like this, member, loan, book copy, what we're actually saying is we'll end up with something like this. If we hadn't already identified the concept of a borrower, or for those of you watching in .NET, iMember or iBorrower, I don't know how you guys speak, but anyway, we actually have recovered or discovered a concept that was actually present in the domain. It allows us to actually make late discoveries about fundamental ideas. In terms of the code, if the code without that decoupling looked like this has cyclic dependencies, the code with the decoupling looks like this. The only difference, and this is one of the important things I want to get across, I am not adding code that does stuff. This code that I've added here doesn't do anything. It's declarative. I'm declaring interfaces. I'm simply saying, I wish to relate like this. There's no if statements, there's no loops, there's nothing that does anything. You don't need more tests or anything like that. It's exactly the same amount of functional code. What is interesting is that if you keep using this technique, over time, your code becomes more decoupled and you get less code that does stuff, because you tend to remove duplication and consolidate things where they go. So this is important. We're not generalizing in the kind of classic sense of adding stuff. We're using speculation to sort things out and actually in the long term reduce things. All we're doing is adding relationship clarifications. So, this is all very well and good. You've made that decision, that's fantastic. Now, obviously, all of your colleagues know it. All of your current colleagues know it. Maybe if you tell them. We have this problem. Let's go back to the nature of time and how we learn. We have a problem of knowledge loss. So, back to Rob's paper, proportion of code written by the current team. Simulated this. Basically, after 20 years, the current team is responsible for 20% of the code. In their heads, 80% of that code base is legacy. 80% was written by other people. We've got a problem with communication here. Now, we're not going to solve this in 2 minutes, but I want to give you the idea that once you recognize you need to be able to propagate knowledge, this tells you something about how you want to structure the other artifacts in your system. But one of the interesting ways, instead of getting bored in documentation, let's talk about an idea that kind of evolved from a lot of patterns thinking that Michael Nygaard introduced a few years ago. ADRs. Can I just have a show of hands? Who has come across architecture decision records? ADRs. Okay, a couple of you. So for the rest of you, hey, good news, new thing. One of the hardest things to track during the life of a project is the motivation behind certain decisions. A new person coming onto a project may be perplexed, baffled, delighted, or infuriated by some past decision. I like his wording here because basically, perplexed, baffled, and infuriated, that's 3 words that are negative, and there's one that might delight them. Generally, that's our response to legacy. Actually, it's a little bit positive. I think it's probably less than 1. But the idea is that that's our general response to legacy. And we've got a problem. Without understanding the rationale, we don't know whether to accept that. In other words, accept complexity even though it has no value and makes our life difficult, or change it and discover that we've broken a very well thought out constraint that somebody thought about. But we've got a loss of knowledge. That's the issue. Learning, a fancier name for learning, is knowledge acquisition. What we need to do is not just knowledge acquisition, but knowledge propagation. How do we communicate this? Well, we could try and hide it in a document that nobody's ever going to read, or we could put it where people will read it. So we want to avoid either of these, and he says, we will keep a collection of records for architecturally significant decisions, those that affect structure, non-functional characteristics, dependencies, interfaces, or construction techniques. Use a technique, Alexandrian patterns, named after Christopher Alexander. It's a derivative form of that. Each record describes a set of forces and a single decision in response to those forces. For the one that I just did, it looks like this. I'm not going to go through this in detail, but I wanted to show you this is what it would look like. It's intentionally, it should fit on a slide, or it should be something simple to type in, typically Markdown, but the idea is it's a record, it's not a document. Record means something small. I can write this on a card or simply on a whiteboard. But the key thing here is structure the package dependencies with respect to the rate of change according to existing backlog. That is my summary of that. That is the decision. I find that some people who use ADRs tend to name things at the wrong level. They will call it package structuring decision. The problem is that's not the decision. That's about the decision. This is the decision. We are structuring package dependencies with respect to the rate of change. So there is an idea here. We can go through this and break it down. But what we're trying to do is capture and communicate. Typically, we will do this as separate records, and they live in your tool, the tool ecosystem the developers use. The default one in this case is GitHub. Okay, write it in Markdown, use it in GitHub. Do not do this in SharePoint. Your developers are not using SharePoint. SharePoint is not, well, I'm not even sure SharePoint is for human beings, but SharePoint is certainly not for people who are involved in development. You have to put, this has to be part of their ecosystem. It has to be something they would use within their IDE or access multiple times a day. It has to have a low barrier to entry. It doesn't matter how perfect another tool is, because if it's another tool, it's not perfect. People won't use it. There are lots of examples I see where people, oh, we've got this great idea, and then they do something that means that developers will actively avoid it. It's a very delicate thing to get this working. You just want people to write a few things, even if they're not writing a full form, even if they're just writing the name. That's good. But the important thing is it should be version controlled, because our system has a history. Let me go back to something here. Status. Accepted. We may change our mind in future. We may discover the future does not look like we thought. And we may change our dependencies, in which case this becomes superseded or deprecated. That's the point of this. It allows these little fragments of documentation to form a larger image that also covers time. So there's a number of ideas we can take this further, but that's this idea of responding to time and loss of knowledge. So I will close with a quote from Grace Hopper that kind of captures a really important idea that we're sort of touching on here. As I said, learning, and I would also say teaching, is about knowledge. It's about acquiring it and then about communicating it, about disseminating it. It's no good as a secret. We want our architecture, and architecture is a shared space where people live and work, and that's how it should feel. But our architecture is also not static, and the people who live and work within it change with time. How do we solve this? This is a non-trivial problem, but at least we start seeing the problem. If you don't see the problem, it's going to be much harder to fix. So let us at least see that. It's more than an important practical art, it is a gigantic undertaking in the foundations of knowledge. Thank you very much.
Thank you very much.